In this video, I'll be covering time complexity and big O notation. My name is Larry, and this is Digital Logic. So what exactly is time complexity? Fundamentally, time complexity describes how an algorithm scales, and that is it. But what exactly does that mean? Let's look at a simple example written in JavaScript. All this function does is print out the numbers from 1 to n inclusively. If we were to execute this function with some value of n, it would take t time. If I were to double the value of n, how much more time would it take? It would take twice as long. Think of it as the amount of additional work that has to be performed as the dataset increases. When we double the value of n, we double the number of iterations within the for loop. Twice as much work will require twice as much time. If we were to triple the value of n, it would take 3 times as long. We can plot this out on a graph where n is on the x-axis and time is on the y-axis, and it would look something like this. This is called linear time complexity, and it is represented as O of n in big O notation. What it essentially means is that as n increases, the time required increases linearly. To be clear though, big O does not tell us if one function is faster than another. All it does is tell us how an algorithm scales, or the rate of increase. We've seen an example of linear time complexity, but there are a lot of different runtimes to be aware of. The following are the most common, but there is no fixed list: constant, logarithmic, linear, linear logarithmic, quadratic, cubic, exponential, and factorial. Runtimes can be combined together, for example, linear logarithmic, and you can have multiple variables within a runtime. N is a commonly used variable, but you can use any variable you want, O of I, for example. Constant time complexity is represented as O of 1. And what it means is that an algorithm will take the same amount of time to execute, regardless of the dataset. Here's a simple example. With this function, it doesn't matter if we increase or decrease the value of n. It will always take the same amount of time to execute. To be clear, we don't know how much time this function will require to execute. All we know is that it won't change if we were to increase the dataset. You might assume that a constant time algorithm would execute very quickly or nearly instantly. And most of the time this is accurate, but not always. Let's take a look at another example. What do you think the runtime complexity is for this function? The parameter n has no effect on the loop, so we have to perform the same amount of work every time this function is executed, regardless of the value of n, so it's O of 1. You may be wondering if O of 1 million would be a more accurate answer. Let's take a look at another example to help clarify this question. Keep in mind, all we're trying to do is to describe how an algorithm scales. All I've done is take the function count and add a second loop within it. So what is the time complexity of this function? We can clearly see that we have to iterate through n twice, so it should be O of 2n, right? For any value of n, this function will take t time. If we were to double the value of n, how much more time would it require? It would require twice as much time as in the base case. Think of it as the amount of additional work that we have to do in relation to the dataset. In the base case, we have to iterate through n twice, because we have 2 for loops, so that would be 2n work. When we double the value of n, each for loop has to do 2n work, for a total of 4n work, which is twice as much work as in the base case. This is why we drop the constant values from the runtime. O of 2n becomes O of n. O of 1 million becomes O of 1. Time complexity does not tell us which algorithm will execute faster. All it does is tell us how an algorithm scales, or the rate of increase, as related to the dataset. As the dataset increases, how much more time will this algorithm require to execute? To help hammer this point home, let's take a look at another example. For this example, we'll just assume that each step runs in constant time. With that said, this function has a linear time complexity, or O of n. But what if we were to split each step into its own loop, like this? Now what would the time complexity be for this function? It would still be linear, or O of n. It doesn't matter that I split up each step into its own loop. And here's another example of the exact same thing. All I've done is exchange the for loops with array functions. In case you're wondering, this still runs in linear time complexity, considering the limited code within the example. What is the time complexity for this function? In this function, we have n divided by 2 iterations within the for loop. But just like in the case where we had 2n iterations, the constant value 2 doesn't provide any meaningful information, so drop it to get the answer of O of n. But don't take my word for it, verify it for yourself. For any value of n, this function will take t time. How much more time would it take if we were to double the value of n? Before we move on, try to remember that runtime complexity does not tell us which algorithm will run faster. All it does is tell us the rate of growth. A linear algorithm may run faster than a constant time algorithm for a specific dataset of n. The only thing that time complexity tells us is that as the dataset increases, the linear algorithm will require more time to execute, whereas the constant time algorithm won't be affected. Let's take a look at another example. What is the time complexity of this function? For each iteration of the outer loop, we have to perform n iterations within the inner loop. You could say that we have to perform n times n work, or n squared work. The big O notation would be O of n squared. Plotting this function on a graph would look something like this. As the value of n increases, it will take even more time to execute this code compared to a linear solution. What is the time complexity for this function? The inner loop will run through n divided by 2 iterations, and the outer loop will run through n iterations. This gives us a total of n squared divided by 2. Drop the constant to get the solution of O of n squared. What is the time complexity for this function? Because both loops depend on separate variables, the correct answer is O of xy. Treating multiple variables as a single value in big O is an easy mistake to make, especially when dealing with arrays. We'll look at an example of this later on. Let's take a look at a more complex example. What is the time complexity of this function? This is a very common pattern. The nested for loop will compare every item in the array with every other item. The outer loop will perform n-1 iterations, but the inner loop is a bit more tricky. For each iteration of the outer loop, the inner loop will perform one less iteration. There are a couple different approaches that we can use to solve this problem. One approach is to calculate the average amount of work the inner loop will do. On the first iteration of the outer loop, the inner loop will perform n-1 iterations. On the last iteration of the outer loop, the inner loop will perform one iteration. The sequence would look something like this. Because it's a sequential sequence, all we need to do is take the smallest number from the sequence, which is 1, and add it to the largest number, n-1, and then divide by 2. This gives us n divided by 2, which is the average amount of work the inner loop performs. Multiply this by n-1, which is the total number of iterations on the outer loop, and this gives us n-1 times n divided by 2. Simplify it to n squared minus n divided by 2. Remove the constant values gives us n squared minus n. Finally, drop the non-dominant term to get the result of O of n squared. You may be wondering why we dropped the minus n term, and I'll go over that in a minute. Another approach that we can use would be to use the sum of integers equation. The equation is n times n plus 1 divided by 2. To understand how it's derived, let's take a look at a sequence counting from 1 to n. If we were to add the beginning of the sequence with the end, it would look like this. So we end up with n divided by 2 pairs, where each pair's sum equals n plus 1, which is how we get the formula n times n plus 1 divided by 2. But our sequence is slightly different, because the inner loop starts with n-1 iterations and decreases to 1. The outer loop will run through n-1 iterations, so this gives us n-1 times n divided by 2, which will reduce to O of n squared after we drop the constant and non-dominant term. So why do we drop non-dominant terms? We've already seen why constant terms don't provide any additional meaning. So when we encounter an O of 2n solution, we drop the constant term and rewrite it as O of n. The same is true for O of 2n squared. Drop the 2 and rewrite it as O of n squared. But let's go back to the O of 2n squared solution and rewrite it as O of n squared plus n squared. If we drop the second n squared term, it doesn't make much sense to keep the lower order term in O of n squared minus n, so drop it. What is the time complexity of this function? Hopefully you're starting to see the pattern here. The number of nested loops dictates the exponent. So the answer to this question is O of n cubed. You can of course have more than 3 nested loops, but it's very rare. What is the time complexity of this function? Since each loop is limited by an independent variable, we can't merge the result to O of n cubed. So the best we can do is O of xyz. What is the time complexity of this function? The inner loop is constant. For each iteration of the outer loop, the inner loop will perform the same amount of work. So the answer is O of n. What is the time complexity of this function? The 2 outer loops should look familiar, as we've already seen a function that followed a very similar pattern. You can use the sum of integers equation, or calculate the average amount of work the second loop performs, and then multiply it by the outer loop. Or you can just jump straight to the solution of O of n squared. But what about the inner loop? The inner loop is constant, so it has no effect on the time complexity. So the final answer is O of n squared. Logarithmic time complexity is represented as O of log n. A function is logarithmic if it cuts the dataset in half with each iteration. But what do I mean by that? Let's take an array of alphabetically sorted characters. If we want to find a specific character in the array, how could we do that? One approach would be to start at the beginning of the array and check every single item in order. The solution runs in linear time complexity since we may have to check every single item in the array. But because the array is sorted, a faster approach would be to start at the center of the array. If the character that we're looking for comes before the selected character, then we know that our character is in the beginning half of the array. Then we just continue to cut the result set in half until we find the character or run out of items to check. This is a very efficient algorithm because the dataset would have to double in size before we'd have to perform one additional iteration. The code for binary search is beyond the scope of this video, so I won't be going over it in detail. The following function will return the index that a value appears in, or -1 if it isn't in the array at all. This is a recursive solution, but you can easily implement it iteratively. So what kind of algorithms are logarithmic? Any algorithm that uses a divide and conquer approach will have a logarithmic component to its time complexity. For example, quicksort and merge sort both have a runtime of O of n log n. Merge sort takes an array and splits it into 2 subarrays. It then takes both subarrays and splits them. It continues this process until each array contains only 1 element. Each iteration we copy n elements into a new array, and we have to do this log n times. That's how we get an n log n runtime. I won't be going over the code for either sorting algorithms because the code is fairly complex and the subject deserves its own video. Exponential time complexity is the opposite of logarithmic and is represented as O of k to the nth power, where k is a constant. In an O of 2 to the nth algorithm, every time the dataset increases by 1, the amount of work doubles. Most brute force solutions will have an exponential time complexity. Exponential time complexity may seem bad, but factorial is even worse, and is represented as O of n with an exclamation mark. For an example, the factorial of 5 would be the product of 5 times 4 times 3 times 2 times 1. An example of an algorithm that would have a factorial runtime would calculate every combination of a set. Since there are n factorial possible combinations, the best runtime we can hope for would be O of n factorial. But in reality, our solution would most likely be worse than n factorial because our function would have some overhead costs associated with it. None of the runtimes that we have gone over are bad. Some problems just can't be solved with anything better. It all depends on the problem that you're trying to solve and the size of the dataset. What you want to avoid is providing an optimized solution that could have been solved faster. The final thing I want to touch on before looking at some more examples is space complexity. Space complexity is very similar to time complexity, only it describes the growth in the amount of memory an algorithm will consume in relation to the dataset. Alright, let's look at some more examples. What is the runtime complexity of this function? If we call fib with the value of 5, that single call will result in calling fib with the value of 4 and 3. For every one call to fib, we get 2 additional calls until the termination condition is reached. This function's runtime complexity is O of 2 to the nth power. Notice that the binary tree that is generated is not balanced. The left branch contains more nodes than the right branch. Because of this, we could specify a slightly more accurate time complexity of O of 1.618 to the nth power, but I really don't think anyone outside of academics really cares. O of 2 to the nth power is accurate enough for big O. What do you think the space complexity is for this function? When we execute this function, we start at fib of 5 and then travel down the left branch, calling fib of 4, and then fib of 3, fib of 2, and then finally fib of 1. Once we reach the termination condition for the left branch, we backtrack to fib of 2 and call fib of 0. This is called depth-first traversal, and it means that we will fully explore the left branch before moving on to the right branch. It also means that we will never have more than n calls within the call stack at once, so the space complexity for this function is O of n. For those of you who may not know this function calculates the Fibonacci value of n, but it is a very inefficient solution, and it could be optimized or refactored to execute in linear time complexity. If you're interested in learning how to do this, then check out my video on the Fibonacci sequence. It's available in Java and JavaScript. When computing the time complexity of an algorithm, you also have to consider the time complexity of any methods that you execute. Let's take a look at an example. In this example, we have a global array. Function A takes an array of items and pushes them into the global array one at a time. What is the time complexity of this function? The array.push method has a constant time complexity. All it does is push the next item onto the end of the array. The outer for loop has to iterate through n elements, so it has a linear time complexity. But what about function B? Now I have to admit, function B doesn't make a whole lot of sense, but let's just go with it. The array.shift method removes and returns the first item in the array, so what's the time complexity of this function? The array.shift method removes the first item in the array, but it also has to shift the remaining items in the array to the left by one index. This means we have to touch every single item in the array every time we shift an item out. This results in a linear time complexity. But because of the while loop, we'll have to do this n times, which will give us the total runtime of O of n squared. Can we improve this function? Absolutely. And here's a simple solution. So I've created a temp array to store the reversed items. The push and pop methods both run in constant time, and the two while loops are linear. So this function does the exact same thing, but it runs in linear time complexity. Let's take a look at another example. What is the time complexity of this function? Let's focus on this line of code. Strings are immutable objects, which means we can't modify a string once it's been created. So what we end up doing here is copy the next character and all of the characters from the old result string into a new string object. With each iteration of the for loop, we'll have to copy more data from the old result string. This is called string building, and is something that you definitely want to avoid. The time complexity for this function is O of n squared. What is the time complexity for this function? This function is identical to the last solution, because we're still performing string building or string concatenation within a loop. It may not look like a loop because of the reduced function, but it's the exact same thing, and it has the same time complexity of O of n squared. If you want to learn more about string reversal, then check out my video on the subject. A link is in the description below. What is the time complexity of this function? This function performs an in-place reversal of the array. So at most we'll only have to touch n items, where n is the length of the array. So the answer is O of n. What is the time complexity of this function? Because both n and m are independent variables, we have to treat them separately, so the correct answer is O of n plus m. What is the time complexity of this function? What is the total number of iterations this for loop will execute? This function will determine if a number is prime by iterating through every number from 2 to the square root of n. So the time complexity would be the square root of n. What is the time complexity of this function? This is a tricky one. The first for loop cuts I in half on each iteration, so the outer loop will execute at most log n times. But we also have to consider the amount of work the inner loop does. On the first iteration, the inner loop will perform n iterations. On the second loop, the inner loop will perform n divided by 2 iterations. On the third loop, n divided by 4, and so on like this. If we were to add all the iterations together, the total would be about 2n. Drop the constant and we get O of n as the final answer. What's the time complexity of this function? The outer loop will perform log n iterations. The inner loop will perform n iterations. So the answer is O of n log n. What is the time complexity of this function, where the array is an array of strings? An optimized sorting algorithm can perform a sort in n log n time. But in this case, what does n reference? Does it refer to the length of the array or the length of the longest string within the array? When you have an ambiguity like this, it's best to avoid using n altogether. So for the length of the array, I'll use a. To sort the array, it'll require a log a comparisons, but that doesn't consider the cost of comparing the strings. To compare two different strings, we'd have to iterate through the characters within those strings one at a time, and we'd have to do it a log a times, which gives us the solution of O of s a log a, where s is the length of the longest string. But what if we were to change the array of strings to an array of numbers? What would the time complexity be now? Assuming an optimized sorting algorithm is used, the sort can be performed with n log n comparisons. Comparing numbers can be performed in constant time, so the time complexity should be O of n log n, where n refers to the length of the array. But in this case, that's not going to happen. The array.sort method allows you to specify a comparison function. If omitted, the items in the array are converted to strings and then sorted by each character's Unicode value. So what we end up getting is O of s a log a time complexity, where a is the length of the array and s is the length of the longest string. If we modify the function by providing a custom comparator, then we can get n log n time complexity, along with the numerical sort order. What is the time complexity of this function, assuming a and b are both positive numbers? What is the total number of times the while loop will execute? The answer is O of a divided by b. What is the time complexity of this function? The maximum number of iterations the for loop will ever execute is n divided by 2, so the time complexity is O of n. What is the time complexity of this function? The variables min and max define the search radius. With each iteration of the while loop, the search radius is cut in half, so the time complexity is O of log n. And for the final question, what is the time complexity of this function? The createDiv function creates a new div, sets its width, height, and position, and then appends it to the document body. This function has a constant time complexity, so we can safely ignore it. However, for each execution of the box function will result in 4 more executions until the termination condition is met. This is an exponential time complexity problem. The base of the exponent will be 4, but what do we set the exponent to? With each iteration, we cut r in half. So at most we'll have log r recursive calls, which will give us the solution of O of 4 to the log r. Time complexity is a difficult subject, but with a little bit of practice you can master it. That is it for this video. If you like this video, then please like, share, subscribe. If you want to support the creation of these videos, then check out my Patreon page. A link is in the description below, and I'll see you in the next video.